Hello. So here we will be simulating the structure, the capacitor, with the area of each plate of 1 centimeter squared and the relative permittivity of 10 as a function of separation distance from 1 millimeter to 1 centimeter. And we will compare this result with the result that we obtained using the classical formula for the capacitance of the parallel plate capacitor. To do so, we open ANSYS electronic desktop and create a new project here and save this project as a capacitor. So we will be using the Maxwell 3D solver. So I create Maxwell 3D project and then choose the solution type. So here I navigate to electrostatic solution solver, click OK. And the first step I need to do is to draw our structure. Okay, so first I will draw the dielectric brick or object like this. And this object, this box, will be made of material that we create. We add new material and call this material material 1 is fine. Relative permittivity, we set relative permittivity to 10. Okay, material 1. Okay, we change the color and make this object transparent. We also rename this object to electric. Okay, so now this material is made of this box is made of our material with refractive index 10. Now we need to change the the position and the size of this object. So by default, ANSYS uses millimeter scaling. If needed, you can change this navigating to the modular type tab and units here. So if you need, you can change this units here. For this project, millimeters is fine. So let us go to the properties of this box and change the size. L and Y are lateral coordinates, so I name them LX and make it so the area is supposed to be 1 centimeter square, so 10 millimeters. 10 millimeters LY. Also 10 millimeters. And the and the thickness D. Right. This is the thickness that we going to change from 1 millimeter to 10 millimeters. So let us move 1 millimeter. So now position. So by default, this position is one of the tips of this rectangular box. So we need to shift it by the distance Lx over 2 minus Ly over 2 and D over 2. Okay. Okay. So as a result, we get this rectangular box distributed like shown like this. So this is our dielectric. I made it more visible so you can see it. Now I create the two plates. Similarly, I choose the box and I choose the box from the library and draw the rectangular box like this. So this is gonna be my first my first plate. So I name it plate 1. This plate will be made of perfect electric conductor. Okay, so perfect electric conductor is just perfect metal. Perfect metal means no losses, no resistance. Change the color to something like this. And of course, I need to change the the size. So the size will be also Lx along x, y along y. The thickness, let's make it maybe 0.1 millimeter, so it's very thick. And also the position, it should be, of course, Lx over 2, y 2, and this z position gonna be d over 2. So I parameterize the position of this box. So when I will be scaling the thickness of the dielectric layer, this plate will be moving automatically. Okay, so I do apply and okay. This is my first plate, which with the thickness of 0.1 millimeter that attaches the bottom side of my dielectric slab. Similarly, I create the second plate. Name it. Give it a name. Plate. Change the color. Okay. Now, similarly, change the the position and the size. D over 2. And thickness 0.1 millimeter. Okay. This is my, oops, something wrong. I got it. It should be minus. For the position, one of them should be minus. Should be negative, isn't it? I see the problem. Our dielectric slab is located wrongly. So I change the position of the dielectric to minus, so to set it symmetrically according to the coordinate origin, like this. And now I can change this to minus d over 2 to create a second slab attaching my dielectric box from the top. All right, so here is the structure. Next, we need to create the area that will be solved numerically, or region, right? I'm navigating to this button here. Create the pad in all directions. For example, in percentage, at least 50%. Okay, so at least 50%. This is our region around the structure. For now, by default, this region is made of air, okay, or vacuum. Vacuum. If needed, one can change the material parameters of this area around. Let me select all faces and hide this region so it doesn't interfere with my project. So what I do, basically, I need to follow this navigation tree or project manager here on the left. So first I create the model, then I need to assign the excitations. Okay, so for this capacitor, I will assign the plate 1 with the voltage, let's say 1 volt, 1 volt. Okay, so this excitation automatically appears in the project manager here. So we've got this excitation on the first plate. The second plate, we also need to assign the the voltage, excitation voltage. We can do -1 or 0. For the capacitance, it doesn't really matter. So +1 volt, -1 volt. So next, what we do, we need to go to the parameters, because essentially what we will be calculating is the capacitance, which is the parameter of the system. Right, so we need to create parameters. We right-click parameters, assign, and then assign the matrix. And in the matrix, we need to enable both the sources, voltage 1 and voltage 2. Then the system will be simulated in correspondence to these two voltages or two excitations. In parameters, we've got this matrix 1 here. Then we need to create analysis. Analysis basically is the way we tell to ANSYS how precisely we need to simulate our system. For example, to make it rather quick, the simulation, we can set 0.1% of the error, and the maximum number of passes just 10. This is enough for this simple project. Okay. Then, as I said, we will be simulating the system as a function of the separation distance between two plates. So we need to go to Actimetrics and tell to ANSYS the parameter sweep, basically. So we add the parameter. For the value, we use d, right, the distance between the plates. As a starting point, we set 1 millimeter, the stop 10 millimeters, and the step of 1 millimeter, for example. Oops, sorry, I forgot to edit. One, stop time, step 1, D, linear step, add. Okay, now it's good. And okay. So now we have this parametric sweep. it's good practice to save the fields in all these cases, in all these steps. So what else is left? We can navigate to Simulation tab and check the mesh settings. If needed, we can increase the mesh, for example, like this. Yeah, so basically the system is ready to be to be solved. We can also add some planes to show up the fields. For example, this XZ plane, I click on this this plane and then add the field, for example, the electric field in the vectoral representation, and also a field in the other plane. For example, the magnitude of the electric field. Okay. Yeah. Next, what we do, we check that our setup is all correct. So we validate it. We see that all the check marks are green. So the project is ready to be executed. And I run the analyze all to simulate the project. It will take a few minutes, maybe 5 minutes for this project. Let me pause the recording. So our project is executed after maybe 3 or 4 minutes. And here is the result. So we already set the planes and the fields in the plane, so we can see the field inside the capacitor and the outside. We notice that for 1 millimeter separation, the field is very homogeneous inside of this capacitor. This is obvious from the vectoral representation and also from the from the absolute value presentation. So we see it's pretty much constant inside of the between the plates, with just a little leakage of the field out from the capacitor. So in order to calculate the capacitance, we need to navigate to the results, right click, and then create electrostatic report. We do a rectangular plot. So here we do our plot as a of the capacitance. For example, so in this case, as you can see, it returns the matrix of 4, 1, 1, 1, 2, 2, 1, 2, 2. We choose the either one, and as a parameter sweep, we indicate D. Right. So create new report. This is the result. So we've got the capacitance of our capacitor from around 10, which like pretty much quadratically decays with the distance between the plates. Compare with our analytical solution. So in our analytical case, the capacitance started from 9 picofarad and also quadratically decays up to 1 or even less than 1 at the separation of 10 millimeters. So we see that the numerical result are a little bit different, right? So for example, around 1 analytical formula gives us the value that just a little bit less than 9. In this numerical case, it's around 10, but the value picofarad and the rest is pretty much the same. We can export this data. So again, if we create the electrostatic report and do data table, the same for the D matrix report. Yeah, we've got this these results for the capacitance as a function of the separation distance. Okay, so in your lab work, you will be asked to export this data to any txt file like this, and then plot these two results, analytical and numerical, on the same plot to see how the numerical result is close to the numerical one, how they agree. So if you remember, we enable saving all the fields for every step of our parameter sweep, which means that now I can simply change this parameter, for example, to 2. And I will see the fields in this case. Again, the field inside is very homogeneous, but more field leaks out from the system, from the capacitor. If I set it to 5, I see that even though the field is still rather homogeneous, we've got some non-homogeneous field distribution by the edge of the plates. Also, the electric field leaks out more significantly from the capacitor, and in the maximum case of 10, you see that the field is rather inhomogeneous, and the vectoral distribution of the field is very unhomogeneous too. So the field distributed very it leaks out from this capacitor very significantly. So yeah, this is the first lab work for our course. Please follow the steps and submit your report as a PDF. And don't forget to compare the solutions, the analytical and numerical, on the same graph. Thank you for your attention.